right, so we've talked about alcohols, we've talked about ethers. Now we're going to move on to thiols and sulfides. So thiols are hydrocarbons that have an SH functional group on them, and sulfides have a carbon chain attached to a sulfur that is attached to another sulfur chain, so RSRs. The first thing we're going to talk about is just the physical properties of of thiols and sulfides. Which of these would we expect to have the highest boiling point? So highest boiling point, what do we usually think about? Yeah, they're intermolecular forces, right? So intermolecular forces, what kinds of intermolecular forces would they have? So intermolecular force types include van der Waals and dipole-dipole and hydrogen bonding. Yep, perfect. So of those three types of intermolecular forces, what would you expect thiols to have? This is a little bit sneakier than usual. So what do I mean by sneakier than usual? Well, I think that a lot of you probably would have said that they have van der Waals. Everything has van der Waals, so they have to have van der Waals. But what else? Well, I think a lot of you probably would say that they have dipole-dipole. So it turns out that they actually don't have dipole-dipole because carbon, hydrogen, and sulfur all have similar electronegativities. Electronegativities. I'm just going to put a period there. Electronegativities. Thiols really only have the ability to do van der Waals interactions. So this alcohol, this thiol, this sulfide, they all have really similar molecular weights, 60, 62, and 62. But which of them would we expect to have the highest boiling point? Great. Alcohols have dipole-dipole and hydrogen bonding as well as the van der Waals. So we would expect this one to have the highest boiling point. Propanol, that's what it's called, has a boiling point of 97 degrees Celsius. What about these two? These two, it would be kind of impossible for me to ask you the question, which of these is going to have a higher boiling point, because they're going to have all the same interaction types. They have literally the identical molecular weight. They should have similar boiling point, right? Turns out that they do. This one's 35 degrees Celsius. This one's 37 degrees Celsius. So that's kind of as far as we're going to get into the physical properties of thiols. One other thing that's kind of a fun fact is they are stinky. If you run into a thiol in the lab or a sulfide, you're going to know it by the old schnoz. You'll be like, ew, I don't want to do that chemistry. Anyway, so now we're going to talk about how to synthesize them, but in real life, you don't want to synthesize them. But on paper, they don't smell, so we can still learn how to synthesize them on paper. All right, so we got a thiol over here. How are we going to synthesize that? I think that you guys probably already can predict this. We would need some type of electrophile, an alkyl halide. That's how we basically, it's the most standard electrophile, and some type of nucleophile. And then what type of solvent would lead to the fastest reaction rate, the most positive type of reaction. Try and put those things in and then come on back. All right, you did it. Thiols are going to be made in a really similar way to how we make alcohols, right? It's an SH instead of an OH. If you look at where they are on the periodic table, they're in the same group. So remember, elements in the same group have very similar chemical and physical, or chemical properties, not necessarily physical. We would break it on that carbon-sulfur bond, and for the alkyl halide, we could just trade out the sulfur for a chlorine. So that makes this our alkyl halide, which is our electrophile, our E+. The partial positives right there, partial negative on that chlorine. Nucleophile, what do we have there? Well, we're going to have SH-. That's a strong nucleophile. It would be attracted to there. And that's how the reaction would work. What kind of reaction was this? Well, it's a primary leaving group. It can't be a unimolecular mechanism. It has to be bimolecular. What kind of solvent is best for bimolecular reactions? An aprotic solvent, correct. So aprotic solvents, the ones we've seen a lot, that I've written at least on the board a lot, include dimethylformamide, DMF, dimethyl sulfoxide, DMSO, and I've also put acetone in there a few times. So acetone, we'll put acetone up here this time, just to give a diverse array of these polar aprotic solvents. So it's as simple as that, just an SN2 reaction of an alkyl halide and SH- to make those thiols. That's how we synthesize them. And we have a little blank right there. Thiols are synthesized through the same reactions that we used to synthesize alcohols. Boop. There it is. Yeah, what about sulfides coming up? Right, so for whatever reason, we really wanted this sulfide, and we started with the alkyl halide. We made our thiol. Now we need to add the sulfur carbon bond so that we can make the sulfide. How are we going to do that? Think about it, write something down. All right, you're back. Great. So we want to make this into a good nucleophile. What do good nucleophiles have in common? They're often negatively charged. Not always, but often negatively charged. So how do we make that turn into that, a good nucleophile? Well, it's an acid-base reaction, right? This was the acid. We lost that hydrogen, so we need a strong base. What we would use is sodium hydride. That's the same one that we used earlier in the chapter. It's a really strong base. It makes HH, which we talked about. It had a pKa of 35. Thiols, generally, it's not on your pKa list, but they have a pKa of 10, so they're even more acidic than alcohols. So sodium hydride would be more than basic enough to make the deprotonated thiol. Again, acid-base reactions move away from the stronger acid. This is the stronger acid, so it would move this way. So we added reagent 1, we made that. Now we have to make the sulfur carbon bond. How do we do that? We need a good electrophile. That's just going to be CH3I. This is an SN2 reaction. We'll do a polar aprotic solvent. We'll add DMSO into the mix just to get a good solvent for that reaction. Those electrons would add there, kicking out the iodide. That would, after we add reagents 2, that would provide the product. Man, that looks really familiar, doesn't it? Well, sulfides are synthesized through the same reactions that we use to synthesize ethers. So alcohols look a lot like thiols, sulfides look a lot like ethers. So shouldn't really feel like new concepts, same old stuff. So hopefully that's how you are feeling.